The world of manufacturing is, well, it's constantly chasing a paradox, isn't it?
Hmm.
How do you cut harder and harder materials faster without just completely destroying your very expensive tools?
Right. It feels like an impossible trade-off. Speed versus longevity. You can't have both.
But today we're diving into a technique that seems to have cracked that exact code. Welcome back to the Deep Dive. This is the show where we take the complex, the super technical, and the highly specific, in this case, advanced CNC machining, and give you the essential shortcut to understanding what truly matters.
And it's a dive into a really specific corner of toolpath generation that has, I'd say quietly, revolutionized high-performance machining over, the last decade or so? We're talking about trochoidal milling.
If you've ever wondered how modern manufacturers tackle things like titanium or the super alloys they use in aviation, this is pretty much the answer.
It is.
And we have a really robust stack of source material here. We're pulling from academic papers, from industry best practices, and some really detailed engineering notes, all focused on this one dynamic milling method.
Our mission today is pretty laser-focused.
It is. We are going to extract the essential facts. How does trochoidal milling work? Why does it give you a genuine superiority over conventional methods? Especially when you're dealing with materials that, eat tools for breakfast. And what kind of specialized software and hardware do you actually need to pull it off?
We want you to walk away not just familiar with the term,
No.
but genuinely well-informed on this whole advanced CNC operation.
Right, because our goal is to explain why this isn't just some minor optimization. It's a fundamental shift in machining strategy.
It's a method engineered specifically to get these incredibly high material removal rates, which means faster cycle times, while, and this is the key, simultaneously extending your tool life. It does this by managing heat and cutting forces like nothing before.
And that combination is, historically, it's a contradiction.
Completely. And that's why this technique is so important.
Okay, let's unpack this. What exactly is trochoidal milling? I mean, it sounds like something straight out of a geometry class, not a machine shop.
That's a perfect observation, actually, because it is entirely based on geometry. At its core, trochoidal milling, or TM, is a specialized dynamic milling method.
Okay.
So instead of the tool following a, predictable straight path like you'd see in traditional slotting or profile milling, the tool moves in this continuously evolving path made up of a series of overlapping circular or spiral cuts.
So the end mill is essentially carving out material by rolling through the cut, rather than just pushing straight through.
Exactly. And this spiral tool path is controlled with extreme precision to ensure the tool has intermittent contact with the material.
Intermittent.
Yes. The method is explicitly designed for high-speed machining, for managing huge volumes of material removal, and it really excels when you're dealing with aerospace alloys or specialized stainless steels, the materials that are notorious for generating extreme heat and causing rapid edge breakdown on your tools.
And when you say intermittent contact, are we talking about like milliseconds of contact followed by milliseconds of cooling time?
That's the idea.
Because the fundamental principles of why this works must be the key to understanding the whole system.
They're the entire foundation. The superiority of TM, it relies on three crucial pillars.
Okay.
First, that intermittent tool contact, which lets you rapidly dissipate heat into the air and, more importantly, into the chips rather than letting it soak into the cutting edge.
Right.
Second, it uses a very high axial cutting depth, or ADOC, which just means we cut very, very deep.
And third.
And third, despite that depth, we achieve dramatically low overall cutting forces because the actual tool engagement is minimal at any single point in time.
That sets the stage perfectly for our first section then, the fundamentals. Let's define the trochoid. And that linguistic background you mentioned, the geometry part, is probably the most useful way to visualize the whole process.
It absolutely is. It grounds a very technical concept in something intuitive.
The word trochoid itself, it comes from the Greek word trochos, which means wheel.
A wheel.
Right. So just imagine a wheel rolling along a straight line. If you put a point on the circumference of that wheel, it traces a curve as it rolls. That curve is the trochoid.
And in our context, the cutting edge of the end mill is tracing that exact curve as it sort of rolls along the path of the slot or the pocket you're trying to create.
And that rolling curvilinear motion is what defines the whole foundational principle of TM when you apply it to cutting metal.
It is. We are deliberately setting up the cut using a high axial depth of cut, high ADOC.
Yeah.
This means we're maximizing the use of the entire length of the cutting flutes, plunging deep into the material, maybe multiple times the diameter of the tool itself.
But at the same time, this is the paradox for the listener, you're saying you must use a low radial depth of cut,
Yeah.
low RDOC.
Yes.
If I need to remove a lot of material, why on earth would I take these tiny shallow slices off the side? Isn't that just less efficient?
That is the critical question, and it really speaks to the limitations of carbide. Yes, moment to moment, taking a slice that's only, say, 5% or 10% of the tool diameter seems slow.
It does.
However, this dual approach, deep but narrow, is engineered to drastically reduce tool wear and heat accumulation. The low radial engagement ensures that the chip thinning effect is maximized, the heat generated is minimal, and the cutting forces never, ever spike.
So we sacrifice the width of the cut, which is what causes high force and high heat,
Right.
in exchange for maximizing the depth, which gives us a high material removal volume over the entire life of the tool.
Precisely. If you're operating conventionally, you might be limited to an axial depth that's equal to your tool diameter. Any deeper, and the forces and the heat from a wide cut become prohibitive, especially in something like titanium.
You just snap the tool.
You would. Trochoidal milling lets you plunge 3, 4, maybe even 5 times the tool diameter deep, using the full length of that cutting edge effectively, all while keeping the tool relatively cool. That's the efficiency game.
And that's the immediate differentiator when we compare it to conventional milling, right? Specifically slotting. If someone is used to standard slotting practices, where the cutter is engaged 100% of its diameter, how does this spiral path really change the game compared to that aggressive straight-ahead path?
Well, what's fascinating here is the mechanics of the engagement itself. Conventional slotting is just brutal on a tool.
Yeah.
You have the cutter fully submerged, engaged for 180 degrees of its circumference. The forces are high, the chip thickness is at its maximum, and that leads to this massive heat concentration right at the cutting edges, which accelerates thermal breakdown and flank wear.
And the heat has absolutely nowhere to go.
Exactly. The tool stays engaged, it stays hot. Trochoidal milling, by contrast, uses that spiral tool path. This dynamic milling action ensures that the arc of engagement is always small, typically under 20 degrees. So the heat and the cutting forces remain consistently low because the tool exits the material momentarily during each little microcycle.
Let's break down that ADOC versus RDOC concept one more time, because it really is the core trade-off. We need to internalize why that low RDOC is so beneficial for these hard materials.
It is absolutely vital. The radial depth of cut, the RDOC, that's the side engagement, is often called the step over or a she.
Okay.
In TM, this is severely limited, like we said, 5% to 10%. This super low engagement keeps the cutting forces minimal, which allows the machine to drive the feed rate really aggressively without overloading the tool.
But the real payoff, the big number, comes from the axial depth of cut, the ADOC.
Correct. To compensate for that shallow side cut and still ensure a high material removal rate, or MRR, we use a very high ADOC. This maximizes the number of flutes engaged in the cut, and crucially, it distributes the workload along the entire cutting edge.
So you're not getting localized wear right at the tip.
Exactly, which is so common in shallow conventional milling. You use the whole tool, not just the bottom corner.
So that spiral trochoidal wave isn't just about moving the tool around. It's about guaranteeing that small, controlled, and consistent engagement throughout the entire depth of the cut. That tiny contact area is the secret sauce.
It is the absolute key. That small, controlled engagement is what drastically reduces the thermal and mechanical shock. We're talking about extending tool life by factors of 5, maybe even 10, compared to traditional slotting. It keeps the cutting action stable, predictable, and crucially cool.
The tooltip isn't just constantly soaking in red-hot material.
It gets to breathe.
Which brings us nicely into our second section, where we can look at the pure mechanics, how the trochoidal toolpath actually works. And that starts with the brains behind the operation, the CAM software. This is clearly not a job you can do manually.
Absolutely not. This level of complexity is why TM wasn't really feasible 30 years ago. It requires specialized computer-aided manufacturing, or CAM, software. And your operators need sophisticated programming skills because these paths are inherently dynamic, they're highly nonlinear, and they require a massive amount of computation to generate the thousands of lines of code that define these tiny micromovements.
We're not talking about simple straight lines and arcs here. These are highly complex calculated curves. So what specific parameters does the CAM software have to actively manage and coordinate to make this motion reliable?
The software has to synchronize several complex variables at once. It defines and constantly controls the feed rate, which is
Yeah.
adjusted dynamically as the tool enters and exits the material. It has to precisely calculate the tool entry and exit areas, which is critical for minimizing shock loading, and of course the ADOC and RDOC
And
parameters.
these aren't static settings, right?
Not at all. Critically, the CAM has to modify these based on the specific material's hardness, the desired surface finish quality, and the known dynamic stiffness and capabilities of the specific CNC machine you're using.
So the machine's control isn't just reading a list of coordinates. It's reading a highly engineered, dynamic motion profile that's designed to maintain a constant force.
Exactly. If the machine is cutting a straight path, the code is simple, G01XY. If it's performing a trochoidal wave, the code is continuously adjusting the X, Y, and Z axes all at the same time to generate that complex rolling spiral.
Okay, let's detail the actual motion. The sources call it circular entry and continuous arc motion. How does the tool engage the material without that shock loading you get from just plunging straight in, especially since we're cutting so deep with that high ADOC?
The tool path is designed so that the initial engagement, when that full depth is achieved, is gradual and circular. It sort of spirals its way down. This circular entry inherently minimizes the sudden load impact on the tool, which is a major point of tool failure. Once it's engaged, the tool maintains continuous arc motion. It is constantly cutting, but because the tool is rolling in that spiral path, the small, controlled arc of engagement ensures the chip load is stable.
And the beauty of this trochoidal wave is that it seems to be self-regulating when it comes to chip evacuation.
Absolutely. The continuous rolling motion is engineered for incredibly efficient chip evacuation, as the tool exits the cut momentarily on the non-engaged side of the spiral.
The open side.
The open side, yes. The centrifugal forces literally fling the chip out of the way, and coolant can get into the cutting zone freely. This prevents chip buildup, which is a major source of heat and those awful chip recutting issues, especially when you're in a deep pocket.
That focus on chip control leads us to another key insight, which is achieving what the sources call constant chip thickness cutting. This sounds almost impossible given the constantly changing geometry.
It is the ultimate measure of success in dynamic milling. The entire objective is to achieve an even, consistent chip thickness throughout the entire cut.
Because in conventional milling, that thickness can spike.
Dramatically, especially at the exit point of the cut, which leads to high forces and instability, what we call chatter.
And when forces fluctuate wildly, you get vibration, a poor finish, and rapid tool failure.
Precisely. TM achieves this consistency by controlling two factors at the same time: that low radial depth of cut and a dynamically adjusted feed rate. Because the tool's engagement angle is so small, that smaller arc of engagement is inherent in trochoidal milling. It fundamentally gives the whole process much higher stability.
So the tool is always efficiently slicing a predictable chip. It's never digging in, never rubbing.
And never overloading the cutting edge unnecessarily.
Let's talk about heat. It's the constant enemy. We should dedicate a moment to the physics of heat management in this spiral motion. How significant is the role of that continuous entry and exit in managing the thermodynamics of the cut?
It's the game changer, especially for superalloys. The continuous spiral motion means that every individual cutting tooth is entering the material, cutting for a very short duration, that small arc of engagement, and then exiting the material and moving into open airspace.
So it gets a brief cooling cycle in the air on every rotation.
Exactly. And this allows for high heat evacuation away from the immediate cutting area through two main mechanisms. Primarily, the heat goes out with the chip, which is exactly what you want.
Okay.
Secondarily, any remaining heat in the cutter is rapidly dissipated into the air, and the coolant during that non-contact part of the trochoidal path. This dramatically reduces the thermal cycling stresses on the carbide edge.
Which means you can run at higher
At
speeds.
much higher surface speeds than would be possible if the tool were continuously engaged and just soaking in heat.
So the stability of the cut is increased, the heat is managed, the chips are efficiently removed. If those three things are happening, the advantages must be pretty compelling. Let's move on to Section 3. The advantages and drawbacks. Starting with the upsides. Productivity and tool life.
The benefits, especially in demanding applications, they provide a substantial economic argument for adopting TM.
Let's start with the fundamental one, the high material removal rate, or MRR. We've established it's faster because you're taking deeper cuts. But how much faster are we actually talking about in real terms compared to conventional methods when you're slotting, say, stainless steel?
When you're roughing a deep pocket in a tough material, The MRR increase can be anywhere from 30% to, in some cases, over 200%.
200%.
It's an enormous range, and it depends on the machine rigidity and the material, of course. But the fundamental reason is that conventional slotting is limited by forces and chip evacuation. It restricts both your depth and your feed rate. TM essentially removes that force bottleneck by limiting the RDOC, which lets the machine maximize its depth and velocity.
And that translates directly to higher productivity.
And significantly shorter cycle times overall.
And that economic benefit hinges entirely on tool longevity. I mean, if you're pushing the machine this hard, the tool better last.
It's the central selling point. That spiral path reduces heat and mechanical stress so dramatically. You have to consider this. Carbide fails fastest from thermal shock and fatigue. By keeping the thermal fluctuations lower and the maximum engagement force reduced, you are delaying the natural thermal death of that cutting edge. Less stress just means you're changing tools far, far less frequently.
Which means less downtime, reduced tool inventory, less operator intervention. That translates directly to cost effectiveness.
Precisely. In a high-volume operation, where an expensive end mill might need to be replaced every few hours with conventional methods, a trochoidal path could extend that to a full shift, or even more. The cost of the complex programming and the specialized machine is often amortized very quickly just through tool cost savings and that reduced downtime.
And finally, there's a quality benefit. If the cut is so dynamic, wouldn't that actually lead to a worse surface finish?
It's counterintuitive, but no. The intermittent cutting action, coupled with the low, consistent heat generation, minimizes two key problems: thermal stresses that cause the material to distort, and chatter. The stability.
Exactly. Because the chip load is constant and the engagement angle is small, the tool isn't subjected to the severe vibration you find in high engagement cutting. This stability leads to a much better, smoother surface finish directly from the roughing operation, which can often save you time in subsequent finishing passes.
Okay, now for the necessary balance. We can't paint a purely rosy picture. Every powerful technique has its limitations. So what are the hurdles to adoption and the practical drawbacks that come with trochoidal milling?
Well, the first and often the highest barrier is complexity. It absolutely requires specialized high-end CAM software. Think Mastercam, Hypermill, GibbsCam, that kind of thing, to generate those precise complex paths.
It's not a cheap add-on.
No.
Yeah.
And critically, you need operators and programmers with advanced skills who really understand the nuances of manipulating parameters like lead-in radii and arc engagement for different materials. It's a very knowledge-intensive technique.
And then there's the limitation based on the hardware itself. Not every machine can handle this motion. That's right. This is where we start talking about machine kinematics. Not all CNC machines are equipped with dynamic milling capabilities or the necessary high-speed servo response and, crucially, look-ahead features.
Right.
Older, slower machines or machines with low-quality controllers, they simply cannot process the massive amount of geometry data in time. That leads to stuttering, which is catastrophic for tool life. You need a machine with high rigidity and high-speed processing power to execute the dynamic motion precisely without lagging behind the code.
And we touched on a fascinating contradiction earlier, which the source material really emphasizes. TM is fantastic for the cutting tool, but potentially damaging to the machine tool itself.
This is a crucial long-term cost factor to consider. While TM saves your end mills, the constant radial motion, the rapid acceleration, and the continuous high-frequency changing of direction in the X and Y axes, well, that can actually accelerate wear and tear on the machine's own internal components.
Specifically the ball screws and slideways.
Exactly. They're subjected to higher average dynamic stress and more rapid load reversals than they would be in traditional straight-line cutting.
So you're paying a premium for a machine that can handle this, and then that very technique accelerates the need for maintenance on its most expensive mechanical parts. It's a continuous force balance.
It absolutely is. This required maintenance has to be quantified and included in any return on investment or ROI analysis. You might save 5 figures a year on carbide, but if your linear encoders or ball screws need premature replacement, that cost has to be factored in.
So finally, when is conventional milling just better? When should we avoid the complexity of TM?
TM is a very specific solution for a specific problem. You should avoid it for wide-open face milling. It's just overkill. For cutting very soft materials like plastics or easy-to-machine aluminum, conventional high-speed milling with a standard tool path is often faster and simpler because the thermal and force limitations that TM addresses just aren't there.
And shallow pockets.
And for extremely shallow pockets, yeah. The programming time might outweigh the cutting time savings. TM strength is in deep cuts, complex geometry, and very hard materials.
Let's move into Section 4, key parameters and the technical deep dive.
Yeah.
We need to go from the conceptual idea to the hard numbers you need on the shop floor. And to make these parameters concrete, let's use the example from the sources, Inconel 718.
Ah, yes.
Here's where it gets really interesting. This material is the benchmark for high-temperature, high-strength applications.
Inconel 718 is the standard for toughness. It work hardens rapidly, it retains heat like crazy, and it's highly abrasive. If you can machine this stuff efficiently, you've mastered dynamic milling.
So let's start with the optimal step over, referred to as N in the sources. Why is 10% the tool diameter the standard starting point for Inconel 718?
That 10% either radial depth of cut is a conservative starting point that's rooted in the geometry of the tool's engagement. If you go much higher than 10%, your engagement angle rapidly increases.
Which in Inconel is bad.
In Inconel, a larger engagement angle translates immediately to higher cutting forces, higher localized heat, and crucially, an increased chance of chip recutting because there's less space for them to get out. Keeping it at 10% or less ensures minimal contact and maximizes that heat evacuation we talked about.
But doesn't using only 10% of the cutter diameter mean the effective feed rate is much higher than what you actually program?
It does. That's a critical technical distinction. When the engagement angle is very small, the phenomenon known as chip thinning is maximized.
Chip thinning.
Right. The programmed feed rate is the speed the tool moves along its path, but the actual chip thickness being generated is much, much smaller than that. So the CAM software compensates for this small engagement by commanding a much higher programmed feed rate, often 200% to 300% of a typical feed, just to maintain a desirable chip thickness.
Okay, so if a programmer sets a starting feed rate of, say, 0.1 millimeters of feed per tooth for Inconel 718, what does that actually mean for the cutter as it's moving across the workpiece?
That 0.1 millimeter feed per tooth, or FPT, is the effective chip thickness we want to achieve. Because we're only engaging 10% of the diameter, the machine controller will likely run the tool at an adjusted, higher programmed feed rate to achieve that desired chip load. This maximizes material removal without exceeding the force limits.
And that's adjustable, I assume.
Highly adjustable based on the tool coding and the specific application, but 0.1 millimeters is the verified benchmark for stability in 718.
And let's address speed. What are the practical RPM ranges?
Due to the incredible heat generated by nickel alloys, the spindle speed has to be managed very carefully. The normal RPM range for Inconel 718 is typically restricted to somewhere between 1,000 and 6,000 RPM.
That's a huge range.
It is, and you might wonder why. The lower end is for extremely rigid setups, or very large tools where your surface speed, your SFM, has to be low to control heat. The higher end is reserved for smaller diameter tools and situations where you have advanced coatings, like specialized Alton, that allow for brief excursions into higher speeds. The key is finding that sweet spot where the heat is minimized, but the cutting action is still aggressive.
Okay, now we need to look at the mathematical heart of this, of predicting stability and tool wear. The engagement angle calculation. This is where the engineering precision really comes in.
It absolutely is. The engagement angle is the precise angle of the tool's cutting edge that is actively engaged in the material at any given moment. Keeping this angle small and, more importantly, predictable is the key to minimizing wear and maximizing stability. If this angle deviates unexpectedly, forces spike and the tool can fail instantly.
And the sources provide a formula for this. How does it connect the tool diameter to the amount of contact?
The formula for the engagement angle is calculated by taking 2 multiplied by the arc of contact and then dividing that result by the tool diameter. It's a simple ratio that quantifies the geometric reality of the cut.
We should probably define that arc of contact again, just for clarity.
Yeah. The arc of contact is essentially the length of the circumference of the tool that is physically touching the workpiece at any given time during a pass. This distance directly dictates how long, in terms of time, the cutting edge spends under thermal and mechanical load in a single rotation.
And since temperature is the primary killer of carbide.
Controlling the arc of contact is synonymous with controlling tool wear prediction. The smaller the arc, the shorter the heat exposure, the longer the tool life. Simple as that.
So the CAM software is effectively managing the X, Y, and Z axes all at once to constantly maintain this calculated tiny arc of contact, regardless of whether the tool is in a straight section or trying to navigate a corner.
Exactly. And for practical application, especially when you're planning a slot, the source mentions a quick calculation. Your slot width must be less than or equal to 1/2 of the tool diameter.
So slot width of his tool.
Right, and that quickly guides machinists to the maximum appropriate tool size for a specific slot, ensuring that enough room remains for the tool to execute that trochoidal motion without engaging too much material.
And finally, there's a reliance on digital tools here. The fact that the sources mention the utility of online resources like the Hoffman Group machining calculator just underscores that even experienced machinists are relying on validated calculations, not guesswork, when they're setting these complex TM parameters.
In trochoidal milling, guessing is catastrophic. The variables, material hardness, coating, flute count, machine stiffness, they're all too interdependent. The calculations account for things like chip thinning compensation and thermal limits in ways that, frankly, human calculation is prone to error. Relying on verified calculators or the output from high-end CAM software is essential for safe, optimized cutting, especially when you're dealing with expensive materials like Incano.
Time to talk about the physical requirements in Section 5. Tooling, machine must-haves, and variations. If the motion is this dynamic and aggressive, it demands specialized hardware just to survive it. Let's start with the tooling, the recommended end mill geometries.
Since TM relies on maximizing that ADOC and surviving rapid thermal cycling, the tools have to be top tier. We are exclusively looking for solid carbide end mills. HSS tools are just completely unsuitable due to heat limitations.
Not even a consideration.
No, and they absolutely need a high-performance coating, think specialized variants of Altin or Tianin to manage the high temperatures generated, even with that intermittent cutting.
Beyond the material itself, what are the structural features necessary to handle the forces, and specifically, the vibration?
The geometry is crucial for two reasons: material removal and vibration mitigation. The tools need a high flute count, typically at least 5 flutes. Often you'll see 7 or 9. More flutes distribute that light chip load across more edges simultaneously, but most importantly, they must incorporate vibration-inhibiting capabilities that are built right into their design.
Explain that vibration-inhibiting feature. This is where variable helix angles come in, right?
Yes, the variable helix angle is a critical design feature. A standard end mill has a fixed helix angle, which means all the flutes enter and exit the material at the same time, generating a harmonic frequency that causes chatter.
That horrible squealing sound.
Exactly. A variable helix tool has flutes that are designed with different angles or uneven spacing. This ensures that the cutting forces are scattered non-harmonically along the flute, which dampens vibration across the entire system and allows the tool to run smoother at higher speeds. This is essential for getting a good surface finish in TM.
Okay, the tools are ready. Now for the machine itself. We already established it needs high rigidity and a high-end controller. What are the specific machine must-haves beyond just being a basic CNC?
Two elements of the control system and hardware are they're non-negotiable for high-efficiency trochoidal milling. First, high-speed look-ahead. This is absolutely paramount because the tool path consists of thousands of short, complex, non-linear moves.
The spiral.
The spiral, yes. The machine controller has to be able to read, process, and anticipate the trajectory of the next dozen or even 100 lines of code in advance.
And why is that look-ahead capability so crucial for tool life?
Without it, the machine stalls momentarily between motion segments. It stutters. This stuttering causes the feed rate to drop unintentionally, which increases the chip thickness unevenly. We lose that crucial constant chip load, and the tool can momentarily rub instead of cup. High-speed look-ahead uses advanced processing power and spline interpolation to smooth the motion, maintaining the optimal feed rate and acceleration needed for that complex spiral path. It guarantees the prescribed RDOC is always met, which, critically, extends the tool life by avoiding those sudden overloads.
So it's not just about speed, it's about computational fluency, making sure the motion is a continuous flow, not a series of stops and starts.
Exactly. And the second must-have is directly related to surviving the heat and debris: high-pressure coolant, or HP coolant. Standard flood coolant often isn't enough, especially in deep slots.
Why does the pressure matter so much in TM?
It's crucial for 3 specific reasons. First, effective heat dissipation. The high-pressure stream just penetrates that small engagement zone better. Second, tool safety by lubricating the contact area. But most importantly, chip removal.
Right.
When you are slotting 3 or 4 diameters deep, gravity and standard flow are just insufficient to get the chips out of the way. You need 500 psi, maybe more, to aggressively blast the chips out of the pocket and prevent them from falling back in and being recut.
Which is a major source of tool failure and heat buildup.
A huge one.
Okay, now let's tie the tooling and the machine together with the tool holder. We mentioned the need for superior rigidity to maintain process stability.
Vibration control affects everything: your surface finish, your tool life, your overall stability. Even the most advanced end mill will chatter if the tool holder is weak. Hydraulic chucks and shrink fit systems are the industry standards for TM because they provide 360-degree contact and superior clamping force compared to basic side lock or spring collet chucks.
What's the difference in rigidity between, say, a standard ER collet and a shrink fit system in this kind of dynamic environment?
The difference is massive. A standard collet system introduces micro gaps and potential for runout. A shrink fit system, by contrast, uses thermal expansion to create an interference fit. The tool becomes essentially a monolithic extension of the spindle,
So it's perfectly centered and perfectly rigid.
as close as you can get. This maximizes the stiffness of the whole assembly, minimizes runout, and provides excellent dampening, which lets you push those aggressive cutting parameters even higher while maintaining stability.
Now, before we move on to applications, the source introduces a fascinating application of this concept: trochoidal turning, taking a milling principle and applying it to a lathe.
It's a compelling variation, yeah. Trochoidal turning uses the same principle, intermittent contact and low controlled engagement, but applies it to grooving operations on a lathe. Instead of the tool just plunging directly into the rotating workpiece, the tool executes small, cyclical, dynamic movements in conjunction with the rotation.
And what's the primary application benefit when you're turning hard materials?
It allows you to do operations like longitudinal and face turning, or radial and axial grooving, on difficult-to-machine materials with dramatically lower forces than you'd see in traditional turning.
Because traditional turning is continuous contact.
It is. High heat, enormous forces on the insert. Trochoidal turning provides a much more stable and less stressful cutting environment for the insert, extending its life, much like TM does for the end mill.
That's a powerful expansion of the concept. Okay, now we know what it is, how it works, what it requires. Let's look at Section 6, Best Application Scenarios and Troubleshooting, starting with the specific scenarios where TM delivers maximum value.
If you really want to see TM shine, you have to look at deep slots and pockets in tough materials.
That makes intuitive sense. That's where the high ADOC and the challenge of chip evacuation are most acute.
Exactly. The aspect ratio, the depth relative to the width, is the real challenge. Conventional methods struggle with forces and chip clogging when you're slotting deeper than one diameter. TM allows you to maintain that low RDOC, managing forces and heat, while achieving 3 or 4 times the tool diameter in axial depth.
Which massively reduces tool wear.
And maximizes tool life when dealing with notoriously tough, expensive stock like Inconel or titanium. In these specific applications, TM is often the only way to achieve roughing speeds quickly without resorting to extremely expensive proprietary indexable milling tools.
Another application you flagged is micromachining specifically, working with thin walls using smaller diameter tools. Why is TM's low heat generation so critical here?
When you machine thin walls, you face 2 primary challenges: tool fragility and thermal distortion. Smaller tools are inherently delicate. The constant small chip load and low forces generated by TM significantly reduce the risk of those fragile tools breaking during the cut, which is a massive cost and quality issue.
And the thermal distortion.
When you're cutting thin features, any excessive heat can cause the material to warp, leading to dimensional inaccuracy. Because TM ensures the heat is rapidly evacuated with the chip and the tool gets its cooling cycle, the residual heat transferred to the workpiece is minimal.
So the part stays stable.
It maintains the structural integrity and dimensional stability of that thin wall, which is critical for precision components.
And finally, its use as a roughing powerhouse. It's positioned as a powerful option for roughing hard or heat-treated materials before you go to the finishing stage.
Absolutely. For roughing operations on hard or heat-treated stock, TM maintains those low engagement angles and minimum tool wear, which allows the machine to maximize its spindle utilization. It is far safer and more predictable to remove the bulk of the material using this dynamic path than with traditional aggressive roughing, which can easily damage the tool or the workpiece due to high forces.
So it gets the bulk out quickly and safely.
And sets the stage for a perfect low-stress finishing pass.
Shifting gears to the reality of the shop floor troubleshooting. This advanced technique must introduce some advanced problems. What are the common issues you encounter when running TM, and what are the quick fixes provided by the sources? Let's tackle excessive tool wear first, since the whole point of TM is to reduce it.
Right. If you are seeing excessive tool wear, it almost always means your geometry or speed parameters are incorrect for the material you're cutting. The most common fix is to lower the engagement angle, adjusting that A below the 10% benchmark, which directly reduces the applied forces on the cutting edge.
And you have to look at your speed.
You have to scrutinize your cutting speed, yes. If the surface speed is too high, it accelerates heat damage. If it's too low, the tool is often rubbing instead of slicing, which leads to abrasive wear.
What if the coating isn't optimized?
That's often overlooked. You have to ensure you're using a material-specific coating. For steel, you might use TCN, but for high-heat alloys like Inconel, you absolutely require a coating that's optimized for high-temperature resistance. Something with high aluminum content, like a specialized Altin, to prevent chemical degradation of the carbide.
Okay, what about poor chip evacuation? A major issue in those deep slots we discussed, even with HP coolant.
Chip clogging is relentless in deep features. If HP coolant isn't enough, you may need to employ an air blast or a mist coolant system directed precisely at the engagement zone to aggressively evacuate those chips. If that fails, the problem is likely in the tool design itself.
So you need a different tool.
You need to use tools specifically designed for evacuation. Look for ones with chip breakers, which segment the chip into smaller, more manageable pieces, or tools with high helix angles, which help facilitate the upward movement of chips out of the pocket or slot.
And what if the surface finish is unstable? You're seeing vibration marks.
Vibration marks are a clear signal of harmonic instability. The easiest fix is to just slow down the feed rate. That immediately reduces the amplitude of the vibration. However, the best structural fix is to utilize those variable helix tools we discussed.
Because they break up the rhythm.
Exactly.
Right.
They scatter the cutting forces evenly along the flute, they break up the harmonic resonance that causes chatter, and that leads to a much smoother finish. You might also need to look at your tool holder setup again to ensure maximum rigidity.
Okay, let's address some common application questions before we wrap up. Does trochoidal milling actually work on softer materials like aluminum? I mean, if it's designed for inconel, is it just overkill for softer alloys?
It's not overkill, it's just utilized differently. Yes, it works very effectively on non-ferrous materials like aluminum, particularly in roughing operations, where the objective is to get the absolute highest metal removal rate possible.
Why is that?
Because aluminum creates very large, stringy chips, the intermittent contact and the high helix angles of TM tools help to break and evacuate those chips more efficiently than standard tool paths would. It prevents that horrible bird nesting and heat buildup.
And finally, a massive question for job shops with older equipment. Can they retrofit older CNCs for these complex trochoidal paths?
The short answer is yes, to a degree. Older, less sophisticated CNCs might not be able to execute the highly optimized, complex 3D paths of modern dynamic milling software. However, it is possible to retrofit these older machines with updated controllers or specialized software modules that enable them to use simplified trochoidal paths for basic roughing operations.
So you can get some of the benefit.
You can maximize the utility of your existing assets, yes, though they will never achieve the MRR of a new machine that has full high-speed look-ahead capabilities.
This has been a deeply technical and I think an incredibly detailed look at a machining technique that is essential for modern manufacturing. Let's try to synthesize everything we've learned in the outro.
Agreed. This is really about geometry controlling physics.
Recapping the key takeaways. Trochoidal milling is a sophisticated CNC method. It uses the spiral tool path for material removal in a series of overlapping circular cuts. It's the premier strategy for high-speed machining, deep slots, and tackling those hard-to-machine materials like Inconel and titanium.
And the reason for its revolutionary success, it hinges entirely on balancing two geometric parameters. By strategically employing a very low radial depth of cut, the RDOC, and combining it with a high axial depth of cut, the ADOC, the process drastically reduces cutting forces, manages chip thickness, and ensures the tool gets that vital intermittent cooling.
Which massively improves tool life and stability.
Right.
So what does this all mean for the shop floor? It means TM offers a major leap in machining efficiency. We're not talking about a slight improvement. It is the optimal choice for roughing tough materials, for generating 3D curved cavities, cutting deep slots, and really any application where vibration and thermal sensitivity are paramount to maintaining quality and tool longevity.
And ultimately, the effectiveness of TM is a holistic system. It hinges on more than just the cutter. It requires sophisticated CAM software, high-performance tooling with advanced geometry like that variable helix, and of course machine capabilities, notably high-speed look-ahead and dynamic motion controls, to execute these complex high-frequency paths correctly. It's an investment in an integrated high-tech process.
And that leads directly to our final provocative thought for you to consider as you wrap up this deep dive.
We have meticulously detailed the immense tool life savings and productivity gains that are provided by trochoidal milling. However, we also established the inherent drawback. The constant high-frequency radial motion puts exceptional and accelerated wear on the CNC machine's internal components, specifically the ball screws and slideways, which have to constantly reverse direction very rapidly.
So the question for industrial planners and engineers is this.
When you're planning for the long-term adoption of this high-efficiency method, how should the cost analysis of accelerated machine maintenance and eventual component replacement be accurately factored against the significant tool life savings that trochoidal milling provides? What is the true optimized lifecycle cost, the ROI on the machine versus the ROI on the tool that truly dictates the profitability of embracing this advanced technique over the next 10 years? That balance is where the future of manufacturing economics really lies.